The following video was recorded live at the conference and produced by the Sound of Knowledge Incorporated. Welcome to the Black Hat Briefings 1999. This meeting was held in exciting Las Vegas, Nevada from July 7th through the 8th. This is videotape number 23, Track C, Taxonomy of Intrusion Detection Systems.
She's manager of the Secure Document Systems Group. Prior to joining Xerox, she was associate director of the Computer Science Laboratory at SRI International. Until August 1998, she was assistant director for Distributed Systems in Defense Advanced Research Projects Agency, better known as DARPA, in their Information Technology Office, where she had oversight of programs on distributed computing, secure network, information survivability, adaptive systems, and software-enabled control. She has also developed and managed DARPA Information Survivability Program and was instrumental in developing DARPA's Information Assurance Program and developed a new research program on survivability. Introduce Teresa.
Thank you. Talk with you online if you'd like to do that. I've been working in intrusion detection for a long time, for a large part of my career, and just recently I've made a career move to Park where I'm not working on intrusion detection, so but I'm still very interested and happy to talk with you about it. So this is the context of the problem. I'm sure you're all very familiar with the problem detecting intrusions in computer systems and networks. But this kind of shows the problem in a larger context where the first thing you need to do is to collect data that you're going to analyze to see whether something suspicious is happening. And so you've got to deploy sensors. And the sensors could be sniffers and audit trails, the usual things that we all use in our intrusion detection systems, which happen to actually be not very good or precise sensors. But you also could develop specialized sensors. Here I've got a decoy, which you could use to collect a different type of information about user activity on a network. Or you could have specialized sensors and probes that you insert in applications or you insert in routers or elements of your system to collect just exactly the information you're looking for. I'm not going to say a lot more about that except to say that it will be very difficult for intrusion detection to get very good if we don't actually build better sensors than we have now. But once you've collected the data, then you're going to send it off to some intrusion detector or perhaps a set of intrusion detectors to analyze that. And they may use a variety of techniques, which I'll talk about in a moment. But then what do you do when you detect something? And this is where there's a big gap. There's a kind of a big vacuum. There's hardly anybody working on, for example, automated response to signals from intrusion detectors. And that's probably today because the commercially available detectors have very high false alarm rates and also high misdetection rates. But you could conceive of a future where you would want to automatically take some action based on what you know from your detectors. And so we did a little bit of research when I was at DARPA on beginning to explore that area. There's some systems that are working on automated response, but beyond that, we also looked at the problem of critical systems, as in the critical national infrastructure, and what they would need in order to respond. And so there it's not just a matter of taking yourself off the net for half an hour while you clean up or something, but there you've actually got to continue operating, and so you may have different modes of operation. So you may be able to switch into a more defensive mode. There may be resources that you can devote to security that were normally being used for other things and so forth. And that's an area I think that's very ripe for innovation. And then other things that people talk about are fish bowls. So you might, as part of your response, kind of create an artificial environment for the attacker so you can further observe him in a place where they're not able to do quite as much damage. And then, of course, cleanup. And cleanup today is a very labor-intensive, time-consuming activity, and I think this is another area where there's plenty of room to do something to make that a more affordable task. So that's kind of the whole context, and I'll be talking now about that detection component, but keep in mind, I think we should be all working on, or many of us should be working on those other pieces of the problem. So data collection, this gets at the sensor problem. Today we have sniffers and we have operating system logs and audit trails, and anybody who's built or used an intrusion detector knows that those things are just not very good. So one of the problems is they're collecting a lot of information that we don't need, and another problem is they're not collecting information that we would like them to collect. So for example, you could collect all operating system calls, which a lot of the audit trails do, or you might prefer to get command line information because that gives you a lot more intuition about what somebody's trying to do, and it's difficult to infer from the operating system calls. But there's a trade-off because there may be attacks that you can only detect through certain sequences of operating system calls. So anyway, there's all these different sources of data, and they have trade-offs in the type of intrusions you may be able to detect, the intuition you can apply to building a rule set to detect them, the operating efficiency of your intrusion detector, and so forth. So, and then degree of privacy invasion, which is something that we can't ignore. So another thing that I've put back here is data reliability. So depending on where you collect the data, it may be easier for the attacker to spoof that data. So if it's not in a protected area, if it's not in a kernel-owned data space, then it may be easier for that data to be spoofed, and so you may want to put less belief in the correctness of that data. My personal opinion is we need to collect data from lots of different places and to tailor the type of sensors we build for the type of analysis that we're going to do. And I'll talk a little bit more about that later. So typical operating system audit record fields, there'll be a subject field telling you who did the action, and a kind of verb field, action field, telling you what was attempted, the object, what's the object of the action, which could be a file or another user, or varies depending on the type of action, and then error code, resource consumption information, and timestamp. The timestamp is somewhat problematic now that we're monitoring distributed resources, and unfortunately a lot of designers of intrusion detection systems design their systems to believe unequivocally in the correctness of the timestamp, not anticipating the clock drift across a large network, and that's one failing of them that can be taken advantage of by the attacker. So my opinion is we should be designing systems to not have an exact notion of time or of what came first and what came second, and to have a little bit more tolerance to inexact time. So what's the state of the art today in intrusion detection? Host-based systems, people try to distinguish between what's a host-based intrusion detector and what's a network-based intrusion detector. My view is that we really don't have network intrusion detectors. We have things that are called network intrusion detectors, and they're called that because their source of data is data sniffed off communication lines. But it doesn't mean that they have any notion of what's an attack on a network or how to detect an attack on a network. Instead, they're detecting attacks on individual machines, and because perhaps they can see many machines at once, they can detect attacks that cross the network, but they're not attacks on the network. This is, I think, a difficult area where we're starting to develop technology that might allow you to detect attacks on a network if we could define what those were and knew what to look for. Knowledge base. So most of the commercial systems are they're looking for things that have already happened before. So they have a rule base or knowledge base of things that have happened in the past, and somebody's gone through those attacks that have happened in the past and picked out the indicators that make you think this attack might be happening again, much like a virus detector is only not quite so accurate. So this has a limitation that we're not necessarily going to be able to discover new attacks in progress using these systems, and they need to be continually updated. Most of them are very limited in the number and type of attacks that they can detect, and part of that limitation has to do with the type of data they're collecting. So it's unrealistic for them to, say, detect fraud in an enterprise when they're not actually looking in logs or in the applications that would give them any indication of fraud occurring. So again, we need to look at sensors and detectors together in order to improve them. And also a high number of false alarms. And part of this is due to the fact that most of them are string matching kind of rules. So they've got simple rules that say, if I'm sniffing off the network and I see this string occur in the stuff I'm sniffing, then I'm going to raise a flag. And unfortunately, that's a very kind of unsophisticated type of analysis. And even some of them that do some very simple statistical analysis usually are doing, looking at 1 or 2 standard deviations from the mean on individual statistics. And that kind of thing is just not good enough. We'll get way too many false alarms. So this is the kind of motivation that, the kind of thing that motivated me at DARPA to look at new research in intrusion detection. And while I was there, we kicked off a fairly large program, which is now even larger. In fact, those of you who are interested, there's expected to be new solicitations coming out this summer and this fall with a lot of money in there for not only intrusion detection, but what they're calling large-scale intrusion assessment, which is the ability of many, many intrusion detectors to collectively work together to get a big picture on what's happening in a large-scale system. So that may be something to think about. But these are some of the research challenges I see. We need to be able to detect a variety of intrusion types, not just the few that that we've already seen, or a few that we can detect using the kinds of sensors that we have today. And this is very important. We need a very high certainty in the findings that those detectors tell us. So if they're raising an alarm, we don't want to waste our time tracking down a false alarm. And if there's too many false alarms, these things are going to be too expensive to use, and they're not going to be worth what we pay for them. And we also need very high certainty when they're not raising an alarm that there's no suspicious activity going on that we would have liked to be notified of. This turns out to be very, very difficult, and I've got some statistics later in the talk to show you how good some of the research systems are as compared to the commercial systems, and there's still a long way to go. Real-time detection, so I think we all agree that we want to know while the thing is still happening or shortly thereafter, not the next morning. And we want to be able to develop a network-wide view. And this is going to be important when we start applying these types of systems to, say, ISPs or telecommunication systems or other elements of the national infrastructure, which are very, very large scale. And they're not interested necessarily in break-ins in end-user systems, but they're interested in attacks that are going to affect their ability to provide service to their subscribers, which is a different kind of thing. And I don't think that we've really spent a lot of time to look at that kind of problem. And we have to be able to work reliably with incomplete data. This is part of living in a network. So we're not going to have access to all our sensors all the time if we have a community of intrusion detectors spread across a very large network. There'll be network partitions, there'll be latencies, there'll be packet storms, there'll be things that will prevent us from getting timely access to our data from our sensors, and we have to be robust to that. We can't have rules in our rule base that will just not flag if some piece of data is missing, but all the other pieces are there. Scalability, so scalability becomes important in very large systems, and some of the methods that we use are really not very scalable. So systems that depend exclusively on sniffed data really don't scale that well when, say, you're going to use them for an ISP, and so you don't see people using them at large numbers of internal routers within an ISP. And the ability to detect unanticipated attack types. And I think this is really important, and this is where I focused a lot of the research when I was at DARPA, because it's easy, it doesn't require research to build a system to go out and find the things we already know are out there. It requires some skill in being able to distinguish the features that occur in the attack that don't occur very often in normal activity. And that's a skill that is very important in reducing the false alarm rate. But that's not research. So I think it's a very interesting research question to say what methods can we use that will raise our suspicions when something happens, an attack happens that we haven't seen before. And it's a very hard problem. And I'll talk a little bit later about some of the methods that have been used there. So, and I won't go through this long list, but there are still a lot of open questions, and I'd say the field is just really in its infancy. So here's my attempt to categorize some of the new methods that are under investigation. First of all, there are methods that are statistical that look at unusual events or unusual combination of events, and that there's a threshold you can define to say how unusual it has to be before you want to look at it. So this is not necessarily going to find all the attacks, but it will raise suspicion when there's something that you probably really would want to look at anyway. Not all of these will be attacks. Some of them may be may be very legitimate behavior, but they may be failures or other things that you'd want to know about anyway. And under that category, there are the usual statistical methods, neural networks, and machine learning, which they're different techniques for pulling out the highly unusual events from a large set of data. And then there are methods to detect activity outside prescribed bounds. And this, I think, is a very promising area. So, for example, there was one project that was called specification-based detection that would, and this was done at UC Davis, where they looked at the privileged programs in Unix, and they wrote a partial security specification for those programs. For example, the login program, they said, should not write files. Should only read from here, should only write from there, and should not do anything else. And so, if you notice, then you can translate those into rules, detection rules, and then if you notice those programs doing something other than that, you can guess that you've been compromised, but you don't have to know what the attack was. So what you're doing is writing rules to identify the effects of an attack that would be common across many, many kinds of attacks without having to know the techniques of the attack ahead of time. So this would enable you to detect unanticipated attack types. And then there's new knowledge-based analysis techniques. Now, the knowledge-based techniques, as I said, will require you to encode rules that look for things that you already know about. But the systems that are used today have very, very simple notions of that. There's some newer techniques being developed in the research that will allow you to specify a rule as a graph over a network, for example. So instead of defining an attack as something happening on a machine, you can define, say, the spread of a virus across a network, for example. And the one difficulty with this is we don't have a lot of intuition about what an attack on a network is, so we need to get some experience using these tools so we can actually write some good rules using them. And then traceback methods. There's a little bit of work going on in building methods to trace back the source of an attack within the network once you've detected it. And I don't have enough time to go into it here, but there was an interesting technique called thumbprinting that was developed at UC Davis. That's a statistical method that looks at a window of activity, and you take a statistical function over that, and you can store it in a database. That function is called a thumbprint, and the thumbprint has the property that if you have a window of activity from over a communication line, say, and you moved your window, say, a few bytes either way, and compute the thumbprint, you'd get very similar values. But if you computed it over different communications, you'd get very different values. So you could use the thumbprint to say, ask somebody, have you seen this thumbprint? And if they did, it's very likely to be the same communication that went through you as went through their machine. So if you're keeping a database of these things, then you can do a query. If enough other people have them, then you can start piecing together where somebody came from. There's other methods being developed using what's called active networks at DARPA, but I don't really have time to go into that. But people are starting to look at techniques for this. Cooperating detectors. I think that when it's possible for intrusion detectors to work together to solve problems, we may be able to use this to reduce false alarm rates. And I think even more interestingly, we can start talking about a community of detectors that starts realizing when something is a problem that can be solved locally, or when something is of larger significance and needs to be reported to some higher authority. So people are now talking about hierarchies of detectors and having, national reporting centers and things like that. But even within say a global corporation like Xerox, where I work, where there's, almost 100,000 employees and there's a global operation, you could envision having detectors at many of their worldwide facilities that are reporting into some corporate-wide center, and as they're able to communicate with each other, they can distinguish between what's something that can be resolved by the local system administrator and what's something that's of much greater concern, that's a real threat to the company as opposed to one of its facilities. One interesting thing about this is that in this picture, this was actually a project that's being conducted at Boeing. And so they've got these orange things, which are sensors, and then they've got these intrusion detectors, and they've got firewalls and filtering routers, and they've built a protocol called the Intrusion Detector and Isolation Protocol, which allows all of these elements to communicate with one another. So if a detector sees something, it can ask a firewall, did you also see this? And if the firewall can say yes or no, and if it saw it, it can further ask another firewall and so forth. So you can kind of track down the path of that intruder, and then say it was a bad guy down here somewhere, then you can take some action as close as possible to the source, rather than say disconnect from the network or something like that. Okay, so I'm going to go over some of the techniques that are being investigated now in the research community. There's this was my work at SRI, statistical anomaly detection, and the idea started many years ago. Looking at user behavior. This was before networks. People were really using, large-scale networks. So this was like in a local area network setting. You would have a detector and it would be monitoring user activity. And we showed that you can pretty reliably detect when it's not the claimed user. So if somebody's logged in under somebody else's name, you can distinguish pretty readily that from a behavior profile that it's not them. And the way it works is you establish an historical profile for what's usual for that person, and that profile is updated over time, and the older data is aged out so that you have a kind of up-to-date view of what's normal for a person. And then you have a short-term profile that's the last 20 minutes or so of their behavior, and you compare those two profiles, and if they're different enough, then you raise an alarm. And we would raise an alarm when they were different by something like 1,000%, because we figured that was about the highest false alarm rate that you could tolerate in a large system. But even with that, we could detect reliably when it was a masquerading user. And then we did some experiments to see whether we could profile programs, and we were successful at doing that. So you can detect the difference in behavior between one program and another. And other people have started doing this for other entities, like processes and systems, like a network node, for example. And this work is being continued at SRI. It's now called Emerald. Some of you may be familiar with it. And there was earlier work that showed that the statistical approach might be successful. With all of these statistical or anomaly detection approaches, there are shortcomings. So for example, if there's abnormal behavior, if there's bad behavior that's normal, so somebody consistently is doing bad things, that's going to be in their profile, and so you're not going to necessarily be able to detect bad things all the time. And the other thing we found was that there are some users who touch everything. I mean, they exhibit every possible behavior, like the sysadmin, and they'd be running these daemons and things under their account, and they're running around the clock, and so you can't get any reliable profile on some users. And that's a pretty well understood result in all kinds of biometrics. So there's other biometrics that have to do with the way you walk, and all of them have there's a class of, a few percent of the population which those things never will work well for, but the rest of them they will. There's been some machine learning approaches. I mentioned two of them here. one at Los Alamos and one at Columbia. The one at Columbia is still going on. And what these things are doing are basically, they're classification techniques, and it's another way of detecting unusual information. Like the statistical techniques, they have to be trained. In this case, the classification techniques are trained on labeled data, so you have to give it samples and labeled, this is good data, this is good behavior, this is bad behavior, and it will learn that. And once you've trained it, then you can give it data for it to discriminate on. And it's been used very, very successfully in fraud detection for credit card transactions. This is a very interesting project, computational immunology. It's the original work was done by Stephanie Forrest at University of New Mexico, and it's another anomaly detection technique, but instead of looking at large scale, like macro behavior, it's looking at system calls. And so and she's profiling processes. So she's looked in Unix at programs like sendmail, and she builds a database of sequences of system calls that occur in sendmail runs that she's done at University of New Mexico. And then once she's built up a database of, say, 1,500 of those sequences, and they're short, like 5 or 6 system call sequences, then she'll do another run and see if it's got any sequences that are not in that database, and if so, she raises a flag. And one interesting thing that she's discovered, and it's related to the title of the project, is that when she did her sabbatical at MIT and she profiled the processes there, they had very different databases, even though they were the same processes. And one of them was LPR, which you would not think would have very different behavior in different user communities, but there's something about the way the users there exercise the program that the database of system calls was very different. So you could even use this possibly, look to me like you could use this to distinguish one, like a Trojan version of the program from a normal version. Anyway, I thought that was very interesting because it was a very lightweight test. Is a string in the database or not? Then model-based detection. This work is being performed at Santa Barbara, where you basically describe an attack as a sequence of events, and once you see some of the events occur, then you can focus your attention on the others. You can kind of hypothesize, well, maybe this thing is happening, and then you can focus your attention on whether the other things are happening. And so it helps you focus your sensors. Say you had programmable sensors, you could start doing a better job at collecting data. And then we already mentioned the graphical detection project. Some applications of these techniques. One of them was done at GTE, where they were applying anomaly detection and signature-based detection to the signaling infrastructure of the GTE telephone network on an experimental basis. And so they had some data collection systems that they'd already built that were worked on their signaling system, and so they just built this analysis on top of those things. And I thought that was the reason. One of the reasons they did that was, I guess, in this Communications Act of 1996, which opened up the communications network to lots of potentially evil competitors who had some access into their control systems, and so now they were concerned about could any of these people be malicious since they were competitors. Another application was for ATM networks. This was done by MCNC, which is a nonprofit institute in North Carolina, and they were looking at IP over ATM, and so one of the challenges there was the very, very high data rates, and they were successful at using, in fact, they used the SRI anomaly detection algorithms, which they tuned for the very high speed, and they also did, they were particularly interested in routing applications, so they built a rule base that was tuned especially for attacks on routing protocols. And I thought that was interesting because if you could build sensors that were unique to the router, that only looked at the router application, not a sniffer that looked at everything going through the router, but something in the router application that only looked at the control messages, you could have a very, very compact log that you could easily look at in real time. And if you have also a specialized rule base to only cared about the routing application. Here you could have embedded intrusion detection ubiquitous in your network. So I think that's a very promising direction for the future. Here's the, again, the Boeing system doing automated response. One of the things that they're looking at in the future is having a variety of different responses you can take to a detected event, and having a cost model. So when you detect there's something happening in your network and you want to take some action, you want to know what's the impact of doing that. And so what they had the idea you could prepare a cost model ahead of time so you could do some kind of analysis and have the least possible impact on the mission of the company or whoever the users of those systems are. So whereas in their first project, all they did was disconnect you for 10 minutes from whatever subnet was originating the problem. Okay, so I want to mention a thing that was started in the DARPA research program called the Common Intrusion Detection Framework. And some of you may have followed this work, and there's a lot of stuff on the web, and that group is continuing. And there's also an IETF activity now that was spawned out of this group. That's a separate activity. And, but let me just tell you about what these folks are attempting to do. One of the things that comes up as soon as you start talking about having a community of detectors out there that can share information is that these detectors are very different from one another. So if I have a statistical anomaly detector and you have a signature-based detector and I want to exchange information with you, we don't speak a common language, and how are you going to interpret the messages I send you, and how am I going to understand the messages you send me? So we wanted to have a common semantics for doing that across a large number of different types of detectors. And we also realized, well, if we could do this, then you could also, once you had all these analysis components, and if they could actually understand each other's outputs, then you could also build a very interesting detector out of several of these components. And so we started working on APIs into these analysis engines, so these A boxes or analysis engines. And we also defined interfaces for what we called E-boxes, which are the event generators or the sensors. And an A-box can also be an E-box in your system. So I could build a system that first uses your signature-based detection system as my sensor, and I can use the output from that as my input and produce another output. So, and then there would be some proprietary control software, which we didn't attempt to specify, and probably some long-term archival storage and that sort of thing. But basically, we just wanted to have some way for these detectors to talk to each other. Well, this proves to be a very difficult task, as you can imagine. And so what I thought might be a 6 or 10-month kind of activity is still going on for many years later. But a less ambitious kind of sister activity has spun off in the IETF, and so they're looking there at some very, very limited ways that intrusion detection systems can interact. So they're looking, for example, at common names for different types of attacks that could be exchanged among detectors and that kind of thing, which is a first step in this direction. But if you want to get involved, Stuart Stanford-Chen is leading the activity in the IETF, I believe, and you can also find out more on the IETF webpage. Yeah, IDWG. Okay, what about the future? And I want to tell you about some of the ideas I had while I was still at DARPA and the program that I started before I left, and for which there will be a solicitation shortly for you to propose research projects under. So looking out to the future, we're looking at someday having many different intrusion detectors out there and deployed widely, and they would be very reliable, and we will be able to believe what they tell us. So now, if we have that kind of a future, what can we do with that? And so, so I called this strategic intrusion assessment. Other people have other words for it, but one of the things that we can do is to suppress false alarms, and basically what I mean here is that if these intrusion detectors can communicate with each other, then they can make some assessment of what's important to a broader community and what's only important locally, so they can suppress certain alarms from propagating up through some hierarchy. The problem here is you don't want to have everything that's detected at the lowest level go up to some national reporting center so that somebody in Washington says, oh, so-and-so's desktop has a virus on it. I mean, that's not the kind of thing you want to know, right? But you do want to know when there's something significant. Well, that kind of raises the question of what is it that's significant? How do you know when something is significant? And so here's where I had this idea of how to infer the intent behind what you might see in this, sea of possibly malicious activity out there. So I thought one way to do that was to come up with hypothesized plans for what somebody might do if they were trying to have some impact on the nation. So what would be the goal of somebody who is trying to attack the United States through its critical infrastructure, through its electronic infrastructure, and how might they carry out, what kind of plan might they have to carry out that goal? And so I thought if you could hypothesize, say, a few dozen goals, you could probably come up with a few hundred plans, and to create those plans, you'd have to have a lot of detailed knowledge of the infrastructure, and particularly the interrelationships among different parts of it, and what depends on what. So if I wanted to, say, cause some decision maker in Washington to make the wrong decision on something, then I may have to change some values in some database somewhere, and I might have to cause a noisy communication on some line that he might use to call somebody to try to verify that what's in the database. And so I may have a plan that causes me to take actions over here and over here and over here to have an effect over there. And unless I have some reason to link those things together, I may just see those as unconnected, disconnected events. But if I had hypothesized that as a plan and I saw those things, then I can say, well, perhaps somebody's trying to carry out this plan, and I say, what are the other elements of the plan, and see, perhaps warn people to look for certain things that might be other elements of the same plan. So there's some technology that's available to help here, although it's not very mature, but it has been used in other domains. There's automated plan generation technology that's being used by the military, for example, in conducting air campaign plans, developing air campaign plans for things like the bombing in Bosnia. So that kind of technology is, people are now starting to think of commercial applications. So how do you plan, say, a manufacturing process and build the assembly line for that? So an automated planner can help with that kind of thing. Workflow and automated workflow systems are kind of sort of similar to these automated plan generation systems. So there's starting to be some technology we can look at. And there's also automated plan recognition technology that's available in the AI community, and this has been used in a number of applications as well, one of them in human speech understanding. So one way that AI systems can understand human speech is they may recognize what a sentence, the beginning of a sentence, and then say what are the possible completions of this sentence, and then look for which ones of those match what actually happens. So we may be able to borrow some of that technology to build tools here. So this is still kind of, like science fiction right now, because the technology we had to start with is so poor. And just to illustrate really how poor it is, I was talking to the Air Force, a guy at the Air Force Information Warfare Center who was talking about the job that he does, and the Air Force has intrusion detectors at all of its Air Force bases, and then they have this place down at Kelly Air Force Base in Texas that gets all of the output from all those detectors. And those detectors, although they're Air Force, are you the guys? Okay, great. So these are old numbers, and you might actually be doing a lot better now. But so this was something Larry Merritt told me, that they alarmed, in a typical 2-week period, they alarmed on 2 million sessions. And 2 million sessions what happens when they have an alarm, because these detectors are sniffers basically, is that they just produce a dump of the entire session that caused the alarm, and then some staff has to go through and look at these sessions and decide, are they possibly suspicious? And that manual review reduced that 2 million to 12,000 suspicious events, and then there's a second tier review that reduced those to 4 actual incidents. And so this is the kind of technology that we're living with. I would say that this technology that the Air Force has is not all that different from the commercial technology. That they come from the same research, and they're very, very similar to each other. Maybe they're using slightly different rules, but you know, if this is the kind of technology that we're starting with, we really have no hope of building this hierarchy that I was talking about, where we could do a large-scale assessment. So you can see we really have a lot to work on, not only building a better detector, but building better sensors to give us better data to analyze. But then, you know, building up from there, how can we recognize when there really is something of concern and not just a bunch of unconnected ankle biters out there? Okay. So if you have that hierarchy, one of the things you might have at any point in that hierarchy that I had on the previous slide is a security detection and response center, and that would be getting reported events from the lower level detectors, and it would be doing some assessment and reporting things up to higher levels. So there's going to be some assessment that filters out things that should not be reported up because they can be resolved locally. And but there's some things that through communication with their peer detectors, they will decide this is possibly a sign of a larger problem, and that will be reported up to a higher level. So that strategic intrusion assessment that I was talking about, using all this automated planning technology, will really be distributed across a network, and lots of these detectors or these reporting centers will have pieces of the analysis for that, so that you know, it's not like there's going to be one place where this all happens. And then as side effects, there could be tracing requests that go out. There could be notifications of people to turn on your sensor over here and that kind of thing. There could be automated response. Now let me tell you a little bit about the evaluation that DARPA and the Air Force did of all these research prototypes. And at the same time, they evaluated a system that was very close, that they considered representative of commercial knowledge-based systems, sniffer-type systems. And the evaluations were intended to drive the research community towards useful solutions. Up till now, we had no way to have an evaluation to compare one method to another, except for the claims of the researchers who built them. So we hope to be able to actually see which ones did better, and which ones should we invest more money in. And also, for the first time, we had a very large set of data that the researchers could use to test their systems, because unfortunately it's very difficult for these folks to find guinea pig networks that are willing to have you install your intrusion detection system, collect all your data, and analyze it. So a lot of them were just not able to do any realistic tests. So the Air Force came up with, last year they had something like 12 or 13 CDs worth of data that was modeled after Air Force-based data, which they had. So it was intended to be very, very realistic data, and they had both TCP dump data and some audit trails from Unix systems. Then they're doing a second round evaluation this year where they have more sources of data, so they've got some NT logs, and I think they may have a firewall log and a router log. And there's two types of evaluation. One is a self-evaluation by the developer at their own facility, and there's a second round where the developer delivers a live system to the Air Force, and at Rome Labs they had a center set up there where they could do live tests. And so the intent was, and all these CDs would have normal data, but there'd be some embedded attacks. So you could not only test their ability to find these attacks, but you could test their false alarm rate. And this was, I think, the first real test of false alarm rates on these systems. The other thing was they created lots of new attacks because we wanted to evaluate how good these things are at detecting new attack types that hadn't been seen before. And just to summarize what they'd discovered, this set of things here represents the best combination of research methods. So in other words, there were lots of different research methods. Some turned out to be very good at some types of attacks and not so good at others. But if you used them together, you could come up with a combination of things that that actually work considerably better than this keyword baseline, which is supposed to be representative of what's available commercially. So you can see the false alarm rate here as a percent. And these are logarithmic, this is a logarithmic scale, so you can see that this is actually quite a bit better than the false alarm rates on the commercial systems. And the detection rate is better. The detection rate down here around 20%, the detection rate up here around 60, 70%. But interestingly, there's also plenty of room for improvement. So although this looks very promising, it doesn't mean we're done. We have a lot further to go. And so, and even here, I think the false alarm rate needs to be much, much better than that. But this is a very good this is a very good slide for a DARPA program manager to have, because you can say, look at the improvement that the investment I made had. You know, so I can go back to the director of DARPA and say, look at all the good things I did with your money, and give me more money, because look at all this over here. So this is like the best result. And that's really all I had to say. I'm happy to take questions if you have some.
Since we're running a little behind time, I think we'll forego the 5-minute break for sodas so that we can break in time for lunch, and we'll go with our next speaker. But before I introduce him, I would like to do another commercial for